Okay, so we are looking at question 1.22 for causal inference and statistics, a primer. I guess I'll just read this. So, a baseball batter named Tim has a better batting average than his teammate Frank. However, someone notices that Frank has a better batting average than Tim against both right-handed and left-handed pitchers. How can this happen? Present your answer in a table. Okay, so hopefully you're reading along in the book, and what this question is talking about is the phenomenon of Simpson's paradox. And Simpson's paradox is basically where the relationship between two variables, here Tim's batting average and Frank's batting average, can reverse when we condition on a third variable. And then if we go on to condition on a fourth variable, it might flip again. And if we condition on a fifth variable, it might flip again, and so on and so forth. So, so here what's going on is we have two variables, the batting average of Tim and Frank. And when we condition on the handedness of the pitcher, the relationship flips between Tim and Frank, right? Where Tim has a better batting average than Frank, but when we condition on the pitcher handedness, then that relationship reverses. Now Frank is doing better than Tim against both of the types of pitchers. Okay, so let's create a table, and now this table is actually just replicated of table 1.2 in the book. Sometimes coming up with these numbers gets a little bit tedious, so I'm just replicating the table that's in the book, and I think that's fine for this question. What we really want to get at is trying to understand why Simpson's paradox is arising. And every time that I hear about this, it takes me a second to wrap my head back around it. It's inherently confusing, but the solution happens to be in the absolute numbers of each of these cells here. Okay, so just notice that. So when we look at the combined here, we see that Tim is doing better than Frank. Okay, now, but why does it arise that when we look at right and left-handed pitchers that Frank is doing better than Tim? Okay, so notice that the pitchers against whom Frank does the best, right-handed pitchers, he has 87 at-bats with, and those for whom he does the worst, he has 263 at-bats with. So in other words, the pitchers against whom he's doing best, he sees the least. Okay, and so when I combined the at-bats for right and left-handed pitchers for Frank, the pitchers against whom he's doing the best make up a small amount of the total at-bats that he's having. Okay, but this situation is actually flipped for Tim. He is doing far better against right-handed pitchers than left-handed pitchers, and he sees more right-handed pitchers. So when we combined Tim's at-bats, the pitchers against whom he is doing the best or better than are representing most of his at-bats, or the majority of his at-bats. Okay, and so then it's not surprising that when we look at the combined results, that Tim is doing better overall than Frank is. Okay, so it's nice to be able to understand Simpson's paradox, but I think where this book is driving towards by presenting Simpson's paradox is that the way in which we look at the data, the assumptions that we're bringing to it, here we might be assuming, or we might be entertaining the possibility that handedness of the pitchers is an important variable here. But the assumptions that we make when looking at the data are giving us can give us completely opposite inferences about the data. And so if we want to make valid inferences, and specifically valid causal inferences, what's causing what, or whatever, then we have to bring valid causal assumptions to the data, right? The data itself is not typically going to provide the way in which you should look at it. You have to be able to bring knowledge from outside of that data, generally, in order to understand how to look at that data. Okay, that's it.